Hello, and welcome to the first webinar in our new series, Lunch, Learn, and Dance, Understanding Radiation. This webinar is meant to serve as an introduction to radiation and radiation safety for people who work in environments where radiation is used, or more generally for anyone who wants to acquire basic knowledge about this subject. My name is Lynn McDonald, and I'll be the presenter for this portion of the webinar. I'll be joined by Angelo Del Torres at 12:30 Eastern, and he will lead us in dance. Also joining me is Maria Costa, who will help monitor the chat. I'll just take a moment to go over the functionality of the Zoom webinar. It's a little different from a Zoom meeting. The audio and video will be from the presenters only. We have found that although you can access audio through the computer or telephone, the quality of sound tends to be better if listening from a computer. There is a chat feature where people can discuss. If you'd like to take a moment to say hello and where you're from, it's a good way to get used to the functionality. There's lots of people online today, so it'd be nice if you had a chance to chat. If you have any questions arriving from the content, could you please enter them under the question and answer section? As the webinar is only half an hour in length and is immediately followed by our dance session, if time does not permit for me to answer the questions during the webinar, I'll be sending out a confirmation email after the webinar, and I'll include that question and answer with them. Also, I will in that email, I'll put in the topics that we covered, the time of the attendance, and a link to the copy of the slides. Some people would like to have that letter to be able to forward to the professional associations. And lastly, I've automatic closed captioning enabled in the slide presentation. If those closed captions are being blocked by your Zoom controls, you should be able to adjust a different way to view the webinar in Zoom to make it easier to see. So in this webinar, we're going to describe what radiation is and how the different types of radiation differ. We'll discuss various ways of quantifying radiation, describe how radiation affects the body, and see how that is used to set radiation dose limits. Finally, we're going to discuss common radiation exposures and list the Canadian regulatory bodies responsible for radiation. Before we start, let's take a look at where radiation is used in Canada. About 15% of the power and electricity supplied in Canada is generated by nuclear power plants. However, of the over 160,000 Canadians monitored annually for workplace radiation exposure, only about 16% are from the nuclear power industry. The remaining 84% come from a variety of sectors, such as healthcare, where nurses, technologists, doctors, and other staff are exposed to X-rays and nuclear substances. In industry, where radioactive substances are used in construction, manufacturing, and mining, and research institutions. But what is radiation? Radiation can simply be interpreted as a form of energy. All matter, whether at rest or in motion, has energy. An object can have potential energy due to its position. An object in motion possesses kinetic energy. With radiation, the energy can take the form of moving particles or bundles of pure energy. Either way, the important thing is that this energy can then be transferred to another material, which can be helpful or harmful. For example, doing work for us or harming our tissues. The type of radiation and its energy will affect how it interacts with matter. Before going any further, we should make it clear that in this webinar, we'll only be discussing high energy radiation. Low energy radiation, also known as non-ionizing radiation, is radiation that is not energetic enough to break bonds in matter. Examples of this type of radiation are radio waves, microwaves, infrared light, and visible light. These types of radiation are all around us constantly. Though there's still research being done to determine if low amounts of these types of radiation can be harmful, it is very important to stress that the health effects that we will be discussing today do not come from exposure to low energy radiation. Non-ionizing radiation interacts very differently with matter than the other types of radiation which we're going to discuss in the webinar. These types of radiation here on this slide do not have sufficient energy to break bonds in matter. If you're interested, we'll be doing future webinars on EMF and Wi-Fi, lasers, and ultraviolet, which will include discussions on forms of non-ionizing radiation. When radiation strikes matter, it interacts with the atoms of matter. So first we have to understand what matter is made of. All matter is made up of little particles called atoms. Atoms, in turn, are made up of protons, neutrons, and electrons. Protons and neutrons make up the nucleus, or center of the atom, and the electrons orbit the nucleus. Atoms commonly have as many protons, which are positively charged, as electrons, which are negatively charged. The positive and negative charges balance each other out, so atoms are electrically neutral. When radiation with high enough energy interacts with one of the orbiting electrons, it can transfer some or all of its energy to that electron, knocking it out of orbit. This leaves the atom with more positive charges than negative charges, resulting in a positively charged atom. The electron is now free and it travels away from the atom. This process of knocking an electron out of orbit is called ionization. In other words, ionizing radiation is radiation which is energetic enough to remove electrons from an atom. So where does this radiation come from? There are two sources of ionizing radiation: radioactive atoms and man-made devices. We have already mentioned what atoms are. They have a nucleus made up of protons and neutrons, and they have electrons orbiting around the nucleus. Most atoms in nature have a stable nucleus, that center part. In other words, the nucleus, it's going to stay intact forever. Some atoms, though, they have unstable nuclei, and they're going to emit radiation or energy to try to become stable. Examples of naturally occurring radioactive atoms include uranium, radium, and radon. We can also create radioactive atoms for medical purposes, such as iodine-131 and technetium-99m. We can also build machines which produce ionizing radiation without the use of radioactive atoms. In this case, we're talking about X-ray units, which include CT scanners. There are several types of ionizing radiation. We're going to go through them now. So there's alpha particles, beta particles, and gamma rays. They're all emitted from the nuclei of radioactive atoms. Neutrons are set free during fission, or the breaking of large atoms like uranium, and X-rays are created by man-made devices. All of these types of radiation have enough energy to knock electrons out of their orbit around the nucleus of the atom, so they're all ionizing. Let's take a closer look at each of them. So alpha radiation is a large particle made up of 2 protons and 2 neutrons. This means that it has a positive 2 charge. Since negative electrons are attracted to the 2 positive protons, alpha particles interact a lot with the matter around them, specifically the electrons that are orbiting nearby atoms. During each one of these interactions, the alpha particle gives up some of its energy, ionizing the matter around it. Alpha particles therefore don't travel far because they lose their kinetic energy quickly through large amounts of ionization they cause. A sheet of paper, or even the dead layer of skin in our body, have enough electrons in them to quickly absorb all the alpha energy, effectively stopping alpha radiation from traveling any farther. Beta particles are smaller and possess only 1 negative charge, half the charge strength that alpha particles have. So they interact less with the matter than the alpha particles. Still, because they possess charge, they do interact with nearby electrons, ionizing matter and losing energy every time they interact. Although beta radiation travels further than alpha, it still doesn't travel very far. It can penetrate our dead layer of skin and deposit energy in our live skin, but generally can't penetrate further into the body. A shield made of plastic, glass, or aluminum contains enough electrons to absorb all beta radiation energy and stop it from traveling farther. X-rays and gamma rays are examples of electromagnetic radiation, just like radio waves, microwaves, infrared, visible, and UV light. They are all what we call photons, or bundles of energy which travel through space at the speed of light. They are pure energy and do not have charge or mass. The difference between these types of electromagnetic radiation is their energy or wavelength or the frequency. X-rays and gamma rays are much more energetic than other types of electromagnetic radiation, as we mentioned earlier. They have enough energy to remove electrons from atoms. Other types of electromagnetic radiation, like visible light or microwaves, they don't have enough energy to do this. The difference between X-rays and gamma rays is their origin. Gamma rays are emitted from the nucleus of a radioactive atom, following alpha or beta radiation. Whereas X-rays are created when electrons hit a target. So that's using man-made machines. The first step in an X-ray production is to accelerate the electrons by sending them through a voltage and electric circuit. The electrons gain a lot of energy and then they're sent crashing into the target, typically a piece of tungsten. As they are stopped in the tungsten, their energy or motion, the kinetic energy they carry, it's lost and it has to go somewhere. If the electrons are energetic enough when they crash into that material, the kinetic energy gets converted into X-rays and they go off in all directions. Like alpha and beta radiation, gamma rays and X-rays are ionizing. But because they don't have mass or charge, they don't interact with matter the same way. They have to crash directly into an electron to knock it out of orbit, whereas alpha and beta can interact without actually hitting the electron. So gamma and X-rays can therefore travel forever in matter if they don't happen to hit an electron on their way through. So no amount of shielding will stop all gamma or X-ray radiation, but the more electrons that are available for it to possibly run into is going to reduce that beam intensity better than something that doesn't have as many electrons. So to summarize, shielding alpha radiation is very easy. A single piece of paper or a dead skin will stop it. That's why alpha is not that dangerous when it's outside the body. It's when it's internal to the body where it's the most dangerous. Most beta particles will get past a piece of paper, but a thin sheet of aluminum or plastic has enough electrons to stop all that radiation. X-rays and gamma rays penetrate materials a lot easier because they have no charge or mass. They might lose a bit of energy in aluminum, but thicker, denser materials like lead are needed to really cut down the beam's intensity. Now we are going to look at the different terms used when we're talking about radiation. One way to measure how radioactive or hazardous a substance is, so again, this isn't X-rays machines, we're talking about radioactive substances, is through its activity. Activity is the rate of radioactive decay. In other words, the number of radioactive decays which occur per second. The unit of activity used in the SI system, which is the system we use in Canada, is the becquerel, named after the person who discovered radioactivity, Henri Becquerel. A becquerel is 1 radioactive decay per second. There's the old unit is the curie, and it's still in use in the United States. And 1 curie is equal to 37 billion becquerels. So there's quite a difference in those 2 ways of measuring activity. Another important property of the radioactive material is its half-life. And the half-life is an indication of how long that substance is going to remain radioactive. It's the time required for half the radioactive atoms in a material to have decayed or to have given off the radiation. After 1 half-life, the activity is decreased by 50%. After 2 half-lives, it'll be reduced another 50%, so that would cut it down to now 25%. So this continues until the material is basically no longer radioactive. Now, half-lives are unalterable. So if you take a look at the most common type of uranium has a half-life of 4.5 billion years, regardless of whether it's attached to other atoms, so like chemically bonded, or if it's a solid, a liquid, or a gas. So you can heat it up, you can cool it down, you can put it under pressure. You're not going to change the radioactive half-life of that uranium. When we discuss radiation dose, so we were just discussing about the material itself, its activity or its half-life. Now, when we're talking radiation doses, we're talking about how much energy is put into an object or a living thing. So we want to measure the amount of energy that's transferred by the radiation to a body. So when you're looking at radiation interacts with those electrons, and it's going to give up some or all of its energy to those electrons as it passes through. So this transfer energy that we're talking about is called a radiation dose. Now, that transfer energy is done immediately when the radiation interacts with an electron. Just like a physical punch, the energy is transferred only when there's contact between the more energetic object, the radiation, and the object that's being hit, like the tissue, or in the case of the boxers, the person being hit. And once that radiation is gone, there's no more transfer of energy. One measure of radiation dose is simply to measure the amount of energy transferred per the unit mass of tissue. And this is called an absorbed dose, and it's measured in gray, with 1 gray of dose being 1 joule per kilogram. 1 gray is a very large dose, so we often refer to milligray, which is 1,000th of a gray, or even microgray, which is 1,000,000th of a gray, when we measure radiation dose. So different types of radiation, the alpha, beta, gamma, X-ray, they produce different amounts of biological damage, however. So remember, alpha is not as damaging on the outside, but if it gets in your tissue, it's more damaging than the other types. So we need a different unit to take this into account. The equivalent dose unit is the absorbed dose in gray multiplied by radiation weighting factor, which indicates how biologically damaging that type of radiation is. The unit of equivalent dose is the sievert, or more commonly the millisievert or microsievert. And the millisievert is again 1/1000th of a sievert. Gamma, X-ray, and beta radiation, they all produce about the same amount of biological damage as they interact with tissues. Their radiation weighting factor is therefore set to 1. 1 unit of absorbed dose of internal alpha radiation, on the other hand, produces approximately 20 times more damage than the same amount of absorbed dose from gamma, X-ray, or beta. So 1 milligray of internal alpha radiation is as damaging as 20 milligray of gamma, beta, or X-ray. The radiation weighting factor for alpha radiation is therefore 20. Equivalent dose takes the biological damage into consideration, making 1 millisievert of one type of radiation equivalent to 1 millisievert of any other types of radiation. But that's not all. Another quantity used to describe radiation dose is effective dose. Like the equivalent dose, effective dose incorporates weighting factors. In this case, the factors are used to account for the varying radiosensitivities of tissues and organs in your body. These factors are unitless numbers called tissue weighting factors. The SI unit for effective dose is the sievert as well. So we have both the equivalent dose and the effective dose being in sievert. So it's important that if you are wearing dosimeter and monitoring that you understand that the difference between is it equivalent dose that's being reported or effective dose. So now that we've talked about the types of radiation, how it's measured, we're going to look at the interaction with the body. So radiation interacts with atoms in the human body the same way it does any other atom. Radiation doesn't know that it's in part of a living thing or a non-living thing. All it does is it transfers its energy and ionizes atoms. So when radiation strikes living tissue, there's a number of outcomes. For one thing, there could be no effect at all. The radiation, for example, could ionize an atom which serves no critical purpose in the body. Since we're all made of more than a trillion atoms, these types of events are very common. On the other hand, radiation can also interact with more important atoms in our body, damaging certain cells. Our body has several layers of defense against this type of event. Primarily, the cells in our bodies have enzymes and proteins whose purpose it is to locate damage and repair it. Cell damage is therefore often not problematic at all. Our cell's secondary defense mechanism is to kill itself if it doesn't have the capacity to repair. We have trillions and trillions of cells in our body, so if a few die because of radiation, it's not a problem. Cells are dying naturally in their body continuously. It's only a problem when we're exposed to a very large amount of radiation over a short period of time, in which part you get a large number of cells dying all at once, and then that would make you ill, and in very extreme cases cause death. That doesn't commonly happen. Finally, there could be damage within the cell, specifically to the chromosomes, which hold genetic information. The instructions for the cell to function properly and how to replicate. It's possible for the damage to a chromosome to be improperly repaired. This low probability event is called a mutation, and those mutations have a certain probability or chance to turn into cancer several years in the future. Getting a radiation-induced mutation in a cell, though it leads to cancer, is what's called probabilistic, that there's only a certain probability that will turn into cancer. Radiation exposure increases the likelihood of developing cancer. The more you're exposed, the greater your chance of getting cancer. But for any one individual, there's no way saying if cancer will occur or not, no matter how much radiation that person is exposed to. Probabilistic events are meaningless on an individual basis. They apply to large numbers of people. So, for example, we know people who smoked their whole life and never get lung cancer. We also know people who get lung cancer and have never smoked. But we do know that smoking causes cancer, right? It's because of this probability. They call it a stochastic effect. So if you take a group of 1 million smokers and you compare it to a group of 1 million non-smokers, there's going to be significantly more cases of lung cancer in the 1 million smokers than in the non-smoking group. Smoking increases the likelihood of getting cancer, but you can never say that an individual got cancer from smoking. It's the same with radiation exposures and cancer. So let's look at what the increased risk of cancer from radiation exposure is. There's this International Commission on Radiological Protection, which is an independent body, reviews scientific literature on radiation and publishes standards and guidelines. They say that the risk of developing a fatal cancer increases by 4% for every 1,000 millisieverts, so every sievert of radiation exposure. And remember, that's a big exposure. These numbers are actually the ones used to set limits on the amount of occupational radiation exposure a worker can receive yearly. So if you consider a person that gets 20 millisieverts of radiation dose per year over a 50-year career, that person would reach a radiation dose of 1 sievert over their whole career, so 1,000 millisieverts. That person will therefore have a 4% increased risk of getting a fatal cancer. The Canadian Cancer Society states that 25% of Canadians will develop a fatal cancer. So this person's chance of developing a fatal cancer will increase from 25% to 29% over a lifetime. So taking those numbers into consideration, along with what might be considered an acceptable risk, limits are set for the amount of occupational exposure a worker is allowed to receive each year. Remembering that we do receive radiation doses just from being outside and from medical procedures. People who work with radiation on a regular basis are called nuclear energy workers, and they can receive up to 50 millisieverts in 1 year, but no more than 100 millisieverts in 5 years. In other words, they should not receive more than 20 millisieverts per year on average. This means a person's maximum lifetime occupational dose over a 50-year career would be 1,000 millisieverts, which could increase that worker's chance of getting a fatal cancer from 25% to 29%. There are different dose limits for pregnant nuclear energy workers who can receive far less radiation during their pregnancy, and people that are not designated as nuclear energy workers. They're only allowed to receive 1 millisievert of radiation per year, which is a very strict limit. So these types of effects that we're talking about, so we just talked about what doses people is acceptable in workplace and things. So now we're going to talk about what effects it might have. And there's two different types of exposures. There's chronic and acute. So most of those doses we're talking is due to chronic exposure, receiving small amounts of radiation over months and years. And we talk a lot about cancer, but there are also things called deterministic effects that if you're exposed to these doses, you're sure that you're going to get them. One of those effects would be cataracts. And the probabilistic effect, or that you're not sure if you'll get it or not, you're increasing your risk of getting it, would be cancer. So an acute exposure is a high dose exposure delivered within seconds, minutes, or days. Like large doses, these do not happen very often. And if exposed, then what happens, you get these deterministic, you will get these effects. These doses, people aren't typically exposed, but if they are exposed to this limit, they would see blood changes, nausea, diarrhea, hair loss, malaise, or feeling really unwell, or they could possibly die. And when we're talking in terms of milligray, if it's less than 250 milligray, you're not going to see any detectable effects, like even if they examine their blood. Over 3,000 milligray or 3 gray, your chance of death is 50% or greater. And over 6 gray, you're pretty much certain to die, but the time it would take between exposure and death depends on the dose. Now remember that a nuclear energy worker is only allowed to receive on average 20 millisieverts per year, and members of the public 1, and that's with those weighting factors in there. And so, and most nuclear energy workers do not, if they're reaching that 20 millisieverts a year, there'd be some look as to why that's happening. That still doesn't happen that often. Also, we're all exposed to radiation constantly. We're exposed to cosmic radiation, which is from the sun and space. There's terrestrial radiation, which comes from soil and rocks. And then when we eat food or we breathe in air, there's radioactive particles get inside us as well. We're also exposed to radiation during some medical treatments. So on average, as Canadians, we would receive about 2 to 4 millisieverts per year from background radiation. And compare that to if you're going back to a person that's not a nuclear energy worker, but might work in a workplace where there are nuclear energy workers in some other location, the dose that's allowed is in 1 calendar year is 1 millisievert. So it's below background amounts. So who takes care and looks after it? And in Canada, the Canadian Nuclear Safety Commission, CNSC, regulates the possession and use of the radioactive substances and radiation devices. So those are ones with the radioactive source. And owners of radiation sources and devices, they might have a license from the CNSC. Now, X-ray systems, which need to be plugged in, they're generally under provincial jurisdiction. In Ontario, the Ministry of Labour has most of the regulations for X-rays in the workplace. There are some medical, dental, that type of thing falling under other ministries. So just a little bit about us before we wrap up this. We're the Radiation Safety Institute of Canada. We're an independent, not-for-profit organization specializing in radiation safety. We do take our independence, we take questions from the public. We look at scientific sources to try to find those answers. Hopefully we know them right off the top of our head, but if not, we'll look it up for you and get back to you. We also have paid courses training for safety officers and things like that. So you can check us out on our website, or you phone the 1-800 number if you have questions about radiation regulations, what it does, different types, anything that you saw in the webinar in more detail. You can always give that number a call and we'll get back to you. So thank you for listening to the webinar, and we'll move on to dance. But for those watching the recording, we'll be ending the recording now. Thank you.